Okay, so this is our final note for this unit. There's a couple more things we're going to work through, but this is the final note that you're going to learn new material and new formulas for. So keep in mind that a test will be coming up in the next few days, and that you're going to want to make sure you've tried all of the assignments before you attempt the test, and that there will be a formula sheet. Make sure you have your formula sheet for your final unit test when you do those. Okay, so efficiency. We've talked a little bit about efficiency already when we talked about simple machines. And basically, when it referred to a simple machine, remember machines were designed to help make our life easier by making a process of doing work easier. And efficiency was basically just saying how well did that machine do in comparison to how well it's rated to do. So its efficiency is how well is it doing the job it's meant to do. And so when we're talking about energy, it's the same thing. If we think about an electrical device that provides some sort of energy related work, we want to know how well is it doing, or what it's supposed to be doing in relation to how much energy is supplied into doing it. And I'll just give you the simplest example for efficiency. So an incandescent light bulb, just as an example, let's move this a little bit. So as an example, an incandescent light bulb, and if you don't know what an incandescent light bulb is, it's basically just an older style light bulb. They're trying to phase them out just basically because of how inefficient they are, but they're the ones that generate a lot of heat. They're hot to touch. So an incandescent light bulb, as our example, it is not very efficient, and here's why. An incandescent light bulb, for 100% energy that we put in it, if we give it 100% electrical energy, just going to make this a little bit smaller. If we give our light bulb 100% electric energy is supplied to our light bulb, out of that 100%, I'm going to redo these. Out of the 100% that's there, 95% of it ends up being heat. And so the remaining 5% is light. And so if we think about this in relation to our definition, efficiency is the ratio of useful energy output to the total energy input. What is a light bulb designed to do? It's designed to give us light. This is our useful energy output, right? When we have a light bulb, it's because we want it to give off light. We don't necessarily want it to give off heat. So this is our useful energy output in this case, and it's in comparison to how much energy we would put in. So if we're putting 100 in and only getting 5 back, it's very, very inefficient. And so here's how you calculate the efficiency of something. So you've learned this already, but the efficiency is just lowercase e, lowercase f. And basically, we're just looking at useful output divided by total input and multiplied by 100. It's kind of exactly like the way that you calculate your mark on a test. If you get, how much did you get on your test out of the total that you could get, times 100 tells you what your percent is. So this is also just saying how well is this light bulb doing what it's supposed to be doing. So we'll look at one example, and this is a pretty involved example, and you'll see examples like this in the future. So pay close attention and try to follow along here. A family sets up an inclined plane as shown in the diagram below. I don't have a diagram here for you, but we're going to make one. If we have an inclined plane, let's say it looks like this, to slide a piano up into the back of a truck. So let's just say here's the back of our truck, here's the inclined plane, and we need to slide a piano up this ramp. The back of the truck is 0.81 meters high, so 0.81 meters is how high off the ground the truck is, and the inclined plane is 3 meters long, and an average force of 1.5 times 10 to the 3 newtons, that should be newtons, Spitz force, is needed to slide the piano up the ramp. So these questions will be broken down for you just like you see here. But what we want to do is first determine the work done by the family. So remember what work is. If you have to consult your formula sheet when you're working through these, it's probably helpful. Work is equal to force times distance. And both of those are given to us. We have a force, 1.5 times 10 to the 3, and we have a distance. So 1.5 times 10 to the 3, and times our distance of 3 meters, was it? Yep, 3 meters. And we end up with a total amount of work of 4,500 Newton meters. And remember, a Newton meter is the same as joules. And so now we've got our work done by the family. But what we want to know is, what's the total amount of work that needs to be done to get this piano? So the goal is, if this was our piano, we had to get the piano from the ground to the top of the truck. So what's the total amount of work or energy that needs to be transferred in order to do that? That's going to be our resulting output, right? To get this piano from here to 0.1881 meters above the ground. So that's our output. Our goal is to get it from here to here. So no matter what, we're going to get it there, but let's just see how we got it there in terms of our energy. So if we were to write this, and I'm going to just type it because it's a little bit quicker. So to determine which is which, our input energy is basically what work the family does to get it up there. Work done by family. And that's what we just calculated in step 1. So that was 4,500 joules. Our output, our useful output energy, is, where do we get our piano from start to finish? We got it from the ground up. So we're working against gravitational potential energy to lift that piano from the ground up to 0.81 meters. And so we need to figure out what that is using this formula, m times g times h. And then we can figure out what the efficiency was for this process. So the first thing is to figure out what was our useful energy output. And that's our mass of our piano, 350 kilograms, times 9.8 for gravity. And the height, the change in height we're getting our piano is 0.81 meters. So 0.81 meters. And so we end up with a gravitational potential energy of 2,778 joules. So 2,778 joules. And so what we want to now know is, what's the efficiency? If we know this is the output and this is the input, we can figure out what our efficiency is. So our efficiency is equal to our useful energy output, which is 2,778, divided by our input, 4,500, times 100. And so our efficiency in this process works out to 62%. So we were 62% efficient in getting this piano from this position to this position using this length ramp. And that's it. So when you're looking at efficiency, you got to look for clues of which is your input energy, what's your output energy, and substitute them into the. And so the final thing that you'll be sometimes asked to do is to draw a energy flow diagram. So if we know what our energy efficiency was, there's a specific type of diagram that is drawn to represent that. And so what we're showing is, what was our total input energy? always this is what it kind of looks like. We have an arrow that shows our total input coming in. And I'm going to make this just a little bit bigger here so that you can see what's happening. Okay, so our total input coming in, and I'll fill that in for now, is our input energy was, what was that? Our input energy was 4,500 joules. So this is what we're putting in order to do this process. So this part of the arrow represents 100% input, always. So what was the amount of input energy? So this width of the arrow represents 100% input. Well, we know that most machines and most people are not 100% efficient at doing what they're doing. So what happens is this arrow, and I'm just going to extend it a bit, oops, ends up splitting off into its percent efficiencies. So we calculated what the efficiency was, and we usually choose a width that represents what the efficiency actually ended up being. So we know that some of it did what it was supposed to do, but a lot of it didn't as well. And so we end up showing arrowheads at the end, showing which out of the 100% that got put into this, what came out of it. So we know that 62% did what it was supposed to do. So this is the useful. And that was a total of 2778 joules. And so if we're starting with 162% ended up being what was useful, this little small part of the arrow just shows what was remaining, what was not useful. So 100 minus 62 tells us that 38% was not useful. So these are things like what makes something not useful. Part of it that's not doing the job it should be for the amount of energy that was put in. Friction along the ramp, possibly heat that's created, would be explaining what some of this represents. And so if we started with a total amount of 4,500 joules, subtract what was useful, tells you how many joules of energy was part of the non-efficient or the non-useful, and that's 1722 joules. So this basically is just taking, once you've calculated the efficiency for anything that you do, this type of diagram will always be drawn like this. So you always have the opposite end of the arrowhead starts as your 100%, and that's your input energy. And then once you know what your percentages are, you just split them off. So because this 62% is larger than 38, we make this part of the arrow a little bit thicker. We show what was the energy amount and the percent for each arm of that arrow. And that's an energy flow diagram. So yeah, you'll be prepared to do some examples just like that for your practice questions.